Okay, so this is the end of chapter 8, and basically this is just kind of a review of everything we've done with proportions, just more examples, give you a little bit more of a better idea of what we've been doing, but nothing really new. So let's start with the first one. The Center for Disease Control and Prevention reported that 22.9% of American adults smoked regularly in 1998. Treat this as a parameter for the population of American adults. So this is our p-value. I just gave it away. What symbol would represent 0.229? P in your book, it's pi. Suppose you take a random sample of 100 American adults. Will the sample proportion of smokers equal exactly 0.229? No, because sampling variability sample proportion doesn't always equal the population proportion. And usually every year somebody points out that you can't have 0.9 of a person if you have 100 people. So, what does the central limit theorem say about how the sample proportion of smokers would vary from sample to sample? So, shape, center, and spread. So, let's double check to make sure this central limit theorem actually works. So, n times p, so 100 times 0.229, again that's 22.9, that's greater than or equal to 10. And then 100 times 0.771, 77.1, that's greater than or equal to 10. So remember that's n times p and n times 1 minus p. So by the central limit theorem, we have an approximately normal distribution. So that's our shape, with a mean of 0.229 and a standard deviation of 0.042. And we'll get there in a second. I'll show you how I got that. So use the central limit theorem to find the z-score corresponding to the sample proportion of smokers equaling 2.25. So again, our mean, it's going to be 0.229, standard deviation 0.229 times 0.771 divided by 100 square rooted. So 0.042. So that's where I got that number. I just did it ahead of time. So now let's find our z-score. So again, this is p hat. So z equals 0.25 minus 0.229 divided by 0.042. Well, 0.5. So use this z-score to compute the probability that the sample proportion of smokers would exceed 0.25. So we're finding the probability that p hat is greater than 0.25. So I already found my z-score. I want to find the probability that z is greater than 0.5. Remember, anytime we're doing a greater than, I'm going to do 1 minus the probability z is less than 0.5. So my formula sheet, I'm going to go to 0.5, 0.6915, so 0.3085. So 30% chance that I get a true proportion of smokers greater than 0.25. Suppose you take a random sample of 400 American adults. How would you expect the probability of the sample proportion of smokers to exceed 0.25 to change when the sample size was 100. So this is kind of what we talked about before. And again, if you want a visual, as your sample size increases, your normal curve gets smaller. So this would be 100 versus 400. So we're looking at a greater than. So, you know, if it was here, you go from this area to just this little guy. So again, as your sample size increases, your variability decreases. So here, the probability would decrease because, again, as sample size increases, variability decreases, causing the area under the curve to decrease. So when you have a less than or a greater than, your probability is really getting smaller. We'll talk about an in-between in a second. But for now, our probability is going to get smaller. So now let's actually calculate that probability. So before we do that, we got to double check, make sure we can use the central limit theorem. So 0.229 times 400 is 91.6. That's greater than or equal to 10. 0.771 times 400 is 308.4. That's greater than or equal to 10. So it's safe to use a normal approximation. Again, just get used to writing that. You're going to be doing it a lot in chapters 9 to 12. So our mean is going to stay 0.229, but now our standard deviation should get smaller. 0.229, 0.771 divided by 400. .021. So now let's find the probability p hat is greater than 0.25 again. I'm going to use the calculator, just kind of, we've been going back and forth. So normal CDF 0.25 to infinity 0.229 0.021. So lower bound, upper bound, mean, standard deviation. Bunch of nines. So now I got 0.1469. So, it obviously got smaller. Did the population size of the United States enter into your calculations? No, because we are dealing with samples. And we'll talk about, really, you don't want your sample to be more than 10% of your whole population size. So even 100 to 400, less than 10% of the population of the U.S. So let's try another example. 51% of the voters in the 2004 presidential election voted for George Bush. Suppose you take a sample of 500 voters from this population. Is 0.51 your parameter or your statistic? 0.51 is your parameter. Okay, it's your p-value. Determine the probability that the sample proportion of Bush voters turns out to be less than 0.5. So before we do this, we want to double check to make sure it's good to use a normal approximation. So again, I'm going to do it kind of up here. 500 times 0.51 and 500 times 0.49. So you always want to use your parameter when you're doing this, not your p-hat. Notice up here I always did 0.229, 0.771, no matter what this number was. So this is 255. That's obviously greater than or equal to 10. And this is 245, so greater than or equal to 10. So we can use a normal approximation. Okay. So our mean here is going to say 0.51. Our standard deviation is 0.51 times 0.49 divided by our sample size, which is 500. Point 022. So we want to find the probability that p hat is less than 0.5. So I'm going to do a z-score. So z is less than 0.5 minus 0.51 divided by 0.022. So z is less than negative 0.45. I'm going to look that up in my formula sheet. Negative 0.45, 0.3264. So, determine the probability that the sample proportion of Bush voters falls between 47 and 55%. So, same mean, same standard deviation, because we're in the same sampling distribution. So now I want to find the probability between 0.47 and 0.55. I'm going to use the calculator on this one. Like I said before, I like to use the calculator for the in-between ones. So normal, CDF, 0.47, 0.55, 0.51, 0.022. So lower bound, upper bound, mean, standard deviation. Oops, 47. So 0.9310. Without doing the actual calculations, indicate how your answer from B and C would change if the sample size were 1,500 instead of 500. So again, this is kind of reiterating what we did for both of these. So let's draw ourselves a little picture. 500 is going to be more spread out. 1,500 is going to be less spread out. So for part B, we're looking at a less than, right? So we're going less than. So for B, the probability will decrease. Because if you're going from a more spread out to a closer together, you have less area under the curve in the tail. So in the tail ends, you have less area. Part C, that in between, you now have more area. So for part C, the probability will increase because you have more area under the curve in the middle. Okay, so that's a good distinction to remember. Just because your variability decreases as your sample size increases, the probability changes depending on what you're looking at versus less than or greater than versus an in-between. Okay, so that's really all of Chapter 8. Like I said, today wasn't too much different, just kind of reiterating everything we've done so far.